So the first part of what I wanted to do today is extend the binomial theorem to talk about trinomials and in general multinomials. So we can look at this thing called the multinomial theorem. If we have time, we'll get to start that, but I wanted to start the next sort of topic in the class, which is Vieta's formulas. Okay? So to talk about Vieta's formulas, we need to establish the fact that a polynomial of degree n has exactly n roots. Okay? Some of which may be the same, and some of which may be complex. Okay? And think back to, I don't know, whenever you take an algebra class or pre-calc, you talk about parabolas, and there's three classes, right? Either they have 0 roots, they look something like that. They could have 1 root, maybe look something like that. Or the most common case, they have 2 roots, they look something like that. Does this sound familiar? Right? It turns out in each of these cases, there are still 2 roots. Here we have 2 real roots, right? With this green one, we still have 2 real roots, but they're repeated. And for this one up here, there's 2 complex roots. Okay? And I can actually reword this and say a polynomial of degree n has exactly n complex roots, right? Because all real numbers are also complex. Remember, complex numbers are of the form a plus bi, where a and b are real numbers. But if I just let b be equal to 0, that's just a set of real numbers, right? This top one is 2 complex roots. Okay. Anyways, so what Vieta's formulas do is they give us a way to interpret a polynomial in standard form. So for example, with a degree 2 polynomial, p of x is ax squared plus bx plus c, in terms of its roots, without having to find the root specifically. Okay? So the questions that we can answer are things of the form, what is the sum of the roots of p of x? And what's the product of the roots of p of x? Okay? And so, knowing nothing about Vieta's formulas, the first way you'd approach this, with at least a parabola, is use the quadratic formula, right? Because we have an explicit closed form solution to finding both of the roots, and then we can find an expression for what the sum of those roots should be and the products of those roots should be. Does that sort of make sense? Okay, so let's take a look. Let's suppose we have p of x is equal to ax squared plus bx plus c, and let's use the quadratic formula. Okay, so we have R1 and R2. One of them uses the plus, one of them uses the minus. And if we want to take the sum of those roots, that square root of the discriminant term cancels out, and we're left with negative 2b over 2a, which gives me negative b over a. Okay, so remember we're dealing with p of x is equal to ax squared plus bx plus c. And what this tells us is that the sum of the roots of this polynomial is negative b over a. Okay, so I don't have to find the roots themselves and then add them. I know just by looking at the polynomial, the sum is negative b over a. If I want to look at the product, right, the square root of the discriminant term also cancels out. And on the numerator, I'm left with b squared minus, in brackets, b squared minus 4ac. The b squares cancel out, and I have a double negative. So I'm left with 4ac over 4a squared, giving me c over a. Okay? So I have an expression for the sum and the product of the roots of p of x without having, these expressions don't involve the roots themselves. It's just looking at p of x is equal to ax squared plus bx plus c. I can find the sum of the product. Okay? But the question is, we did this using the quadratic formula, which only applies to polynomials of degree 2. So how do we expand this to cubic polynomials? We can't, at least not by using the quadratic formula. So there's another way we need to look at this. Okay? So again, let's consider a polynomial of degree 2. And let's suppose it has 2 roots, R1 and R2. And again, they might both be complex. They both might be the same thing, whatever. But we know there's two roots. Let's say they're R1 and R2. Then we know we can write p of x as some scalar constant times x minus r1 times x minus r2, right? Because roots just mean when I plug in r1 or I plug in r2, the function is equal to 0. Is that clear? Okay, so I know I can write it as a times x minus r1 times x minus r2, but I also know I can write it as ax squared plus bx plus c. Okay, so what I do is I expand out this product of x minus r1 times x minus r2 and see what we get, right? So I have ax squared minus a times, using FOIL, I have x times negative r2 plus x times negative r1. So I get negative r1 plus r2x. And the last term I get negative r1 times negative r2, giving me positive a times r1 r2. Okay? And so what I do is I compare this to what I had with ax squared plus bx plus c. And I notice the a's match up, right? I have a and a, so that doesn't tell me anything. I have that b is equal to negative a times r1 plus r2. And I have that c is equal to a times r1 r2. Right? And so by doing a little bit of rearranging, I find that r1 plus r2 is equal to negative b over a, and r1 times r2 is equal to c over a. Okay? And it's not a coincidence, those results match up with what we got with the quadratic formula. But here we didn't use the quadratic formula at all, and this logic can be extended to polynomials of degree 3, degree 4, and just an arbitrary degree of polynomials. Is that clear? So again, to reiterate, what we did was we said that we know that a polynomial of degree 2 will have two roots. Suppose they're r1 and r2. I can write this polynomial as a times x minus r1 times x minus r2. I wrote out the expansion and compared coefficients, right? Ax squared minus a r1 plus r2x plus a r1 r2, and compare that to ax squared plus bx plus c. Okay? And I solved for the sum and product of the roots without using the quadratic formula. So this is what we call Vieta's formula for degree 2 polynomials. Okay? And so what we'll do is generalize this to polynomials of degree 3 and then an arbitrary degree. Okay? So by looking at p of x is equal to 4x squared plus 3x plus 3, I can immediately see that the sum of the roots is negative 3 over 4, and the product is 3 over 4. Okay? I didn't need to compute the individual roots themselves. This just tells me what the sum and products of the roots are without having to know the actual roots. Is that clear? Any questions with this? Okay, so now let's look at degree 3. Okay, so suppose we have some cubic polynomial of the form p of x is equal to a3 x cubed plus a2 x cubed plus a1x plus a naught. And let's assume it has three roots, r1, r2, and r3. And so we can write these two equivalent expansions, one in terms of powers of x and their coefficients, and one in terms of a3, which is the leading coefficient, times x minus r1, x minus r2, and x minus r3. And now we use very similar logic as what we did when talking about the binomial expansion, right? So when we're multiplying out x minus r1, x minus r2, and x minus r3, we need to take one element from each of the parentheses, right? So we have multiple options here. Either we can just choose 3 x's and none of the r's, giving us x cubed, or we can choose 2 of the x's and 1 of the r's, right? And so the ways I can do that, I would have x squared, then I can either choose negative r1, or negative r2, or negative r3. So that gives me minus r1, minus r2, minus r3, x squared, which is what I get here when I factor out the negative sign. Or, when multiplying these three parentheses, I could just take one of the x's and then 2 of the r's. So if I factor out an x, I'll get negative r1 times negative r2, or, so plus, negative r1 times negative r3, or negative r2 times negative r3. All of that times x. So I get this expansion here. r1 r2 plus r1 r3 plus r2 r3 times x. So far I've looked at the cases where I choose 3 x's, 2 x's, and 1x. Lastly, I can choose no x's and 3 of the roots, right? And so I'll just have negative r1 times negative r2 times negative r3. And so what this tells me is that the expansion looks like p of x is equal to a sub 3 times this entire thing. X cubed minus r1 plus r2 plus r3 x squared plus r1 r2 plus r1 r3 plus r2 r3 x minus r1 r2 r3. Okay, because I know I'll either choose 3x's or 2x's or 1x or 0x's. In each of those 4 cases, I found what the coefficient on the power of x will be, and I sort of just write out that expansion. Is that clear? And so I can, again, find these relationships in terms of the sum of the roots and the product of roots in terms of the coefficients a0, a1, a2, and a3, just by doing some comparison. Right? I know I want to compare this quantity up here to this quantity here. And so doing so, I will see things like negative a3 times r1 plus r2 plus r3 is equal to a2, giving me this result. And I do that for all of the other coefficients. So I find that, for example, r1 r2 plus r1 r3 plus r2 r3 is equal to a1 over a3. And I also have what the product of the roots is. Is that clear? So for each of these things that we call symmetric sums, okay? Symmetric sums. Why are they symmetric? Because it doesn't matter if we swap, for example, r1 and r2, or r2 and r3, or r1 and r3. The product of them all, the sum of them all, and then this weird one in the middle, r1 r2 plus r1 r3 plus r2 r3, the values of those won't change if I swap the values around. Is that clear? So those are called symmetric sums. So I have some relationship between all possible symmetric sums and the coefficients of the polynomial. And so this is what we call Vieta's formulas for a polynomial of degree 3. Is that clear? So any questions with all of what we just talked about? Yeah?
Can you generalize this for any polynomial?
We're about to do that. Yeah. Okay. And so I guess to elaborate a little bit more on the degree 3 case, each successive term is some product of the roots taken in different quantities at a time. Right? So the sum r1, r2, r3 is a sum of the product of the roots taken one at a time. So I took all possible groups of one of the roots, so just the roots on their own, and took the sum of them. This sum here, r1, r2 plus r1, r3 plus r2, r3, is the sum of all possible products of two of my roots, right? So there's 3 choose 2, or 3 ways I can choose 2 of the roots, right? I have r1, r2, r1, r3, and r2, r3, and I sum all of those. Lastly, the product r1, r2, r3 is, a sum of the product of the roots taken 3 at a time. But if I take 3 of them, and there's only 3 roots, there's only 3 choose 3, or one way I can do that, which is just r1, r2, r3, which is why there's just one term in the sum. Okay? So the number of ways I can choose one of the roots at a time is 3 choose 1, which is why I'm adding 3 terms here. The number of ways I can choose 2 terms at a time is also 3, which is 3 choose 2, which is why there's 3 terms in this sum. And the number of ways I can choose 3 roots at a time is 3 choose 3, which is 1, which is why there's only 1 term in this sum. Is that clear? So this has a relationship with the combinatorial term that we saw before, and you can also see the relationships between this and binomial theorem. And we'll talk about that in just a second. So what I want you to work on for a minute or two is, without manually expanding out, p of x is equal to a x minus r1, x minus r2, x minus r3, x minus r4, without manually doing FOIL like 4 times, determine Vieta's formulas for polynomials of degree 4. So what we want to do is find some relationship between the sum of the roots and the product of the roots, and all of the other symmetric sums of a polynomial of degree 4 and its coefficients. So something in terms of a4, a3, a2, a1, and a0. So let's take a look. Okay, so we know this polynomial will look something like a4 times this expansion of the product of x minus each of the roots. And so in the first case, if I choose 3 x's and one of the roots, I know I will either have r1 or r2 or r3 or r4 on its own, right? So here I am choosing 3 x's, 1 r, right? And that's why there's 4 choose 3, which is 4 terms in this sum. In the next case, I'm choosing 2 x's and 2 r's, which is why there's 4 choose 2, or 6 terms in this sum. In the next one, I'm choosing 1x and 3 roots, which is why there's 4 choose 1, or 4 terms in this sum. And in the last one, I'm choosing no x's and 4 roots, which is why there's 4 choose 0, or 1 term in this coefficient. Okay? So putting all of this together, I have that p of x can also be expressed as a4 times x to the 4 minus the sum of the roots, x cubed, plus this term over here, whatever that is, r1, r2, plus r1, r3, plus dot, 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 x squared, minus this term here times x, plus r1, r2, r3, r4. Is that clear? So I have this term here, plus product. So r1, r2, r3, r4. So what's something you noticed about the sign on the sum of the roots? In both the degree 4 case, the degree 3 case, which was up here, and the degree 2 case. What did you notice about the sign on that term? Yeah, the signs always alternate, but the coefficient on the sum of the roots is always negative. Okay? And then they alternate because we're varying the number of roots and x's, and as we decrease or increase the number of roots each time, since all of the roots are negative the root, we multiply by -1 each time, which is why it oscillates. So the first term is negative, the next is positive, the next is negative, and the following is positive. Is that clear? So that's what the final expansion of a polynomial of degree 4 would look like. So if I'm given, for example, f of x is 5x to the 4 plus 3x squared plus anything, it doesn't matter what goes here as long as it's a polynomial, and it's as long as it's a polynomial of degree 2, I know the sum of the roots is going to be -3/5. Is that clear? So sum of roots is -3/5. Right? Because the sum of the roots is just negative the second coefficient over the first coefficient. Right? Negative a3 over a4. Is that clear? So it doesn't matter what the rest of the polynomial is. All I need is the first two coefficients, a3 and a4. Is that clear? So given some polynomial, degree 4, or degree anything, I can easily determine what the sum of the roots is and what the product of the roots is. Is that clear? So if I were to give you, we'll do it after this. So first, let's generalize Vieta's formulas to polynomials of any degree. Okay? So for example, let's say we have p of x is equal to an x to the n plus an minus 1 x to the n minus 1, so on and so forth, all the way until a1x plus a0, right? we can generalize this to factoring out an in the front, taking the sum of k, our exponent, going from 0 to n, of -1 to the k, because our terms alternate in parity, or not parity, rather the sign. And what we write is that we're taking the sum of the products of the roots of p of x taken k at a time. Is that clear? So to write this out for, I don't know, p of x is some second degree polynomial. The sum would look like a2, now -1 squared, or I can look at -1 to the 0 first, right, because k starts at 0. The sum of the products of the roots of p of x taken k at a time. So what does that look like? Oh, sorry, taking 0 at a time. So how many ways can I choose 0 of the roots and then multiply them and then add that? What is the product of none of the roots? One, right? So I leave this as 1 times x to the 2 minus 0, which is x squared. Now plus, k is now 1, so I have -1 to the 1. Now what's the sum of the products of the roots of p of x taken 1 at a time? Now that's just the sum of the roots themselves, right? So then this would be r1 plus r2 x to the 1. And then our next term would be -1 squared. What's the sum of the product of the roots of p of x taken 2 at a time? Well, that's just the product of the roots, right? So then I have here r1, r2, and I have no x term there, right? Because that's the last term. So the definition holds up. Okay? But the algebraic definition isn't as important. What's important is realizing how this pattern works and being able to apply it to problems that you haven't seen. Okay? But in general, is everyone okay with the idea of what Vieta's formulas say? Any questions? Because I know we just went over a lot. Okay? So pretend I gave you this polynomial p of x is equal to x to the 100 minus 100 x to the 99 plus 1. What's the sum of the roots of this polynomial? Yeah, 100, right? Because it's negative the coefficient on the second, the negative of the second coefficient, which is negative of -100, divided by the coefficient on x to the 100, which is just 1, which gives me 100. What's the product of the roots of this polynomial? 1, right? Because it's 1, which is this last term, divided by the coefficient on x to the 100, which is 1, which just gives me 1. Okay? So is everyone okay with why the sum of the roots is 100 and not -100? Because the way the formula is defined, you take the negative of that number to find the sum of the roots. Okay? And fun fact, after we did that example, if you go and look at the diagnostic of the class, we've covered how to do every single one of those questions. And I think we've actually done most of them, if not all, as examples in lecture. You can do all the diagnostic now, which is interesting. So what I want to do now is look at some examples of some like contesty questions that use Vieta's formula. And I think they're kind of interesting. Sound good? But is everyone okay with this? Cool. I'll leave this in the slides. I'd rather do the example, but what this sort of talks about is if all the roots are the same, then Vieta's formulas are just the same as the binomial theorem. Okay? Like if you take the sum of 4 roots and all of the roots are equal to c, then that sum is equal to -4 times c, or 4 times c. If you're taking 2 roots at a time, and they're all the same, then each of those products is equal to c squared. And if we have 4 choose 2 or 6 of those products, I'll have 6c squared. And I keep doing this. Right? So this just shows how binomial theorem is a simplification of Vieta's formula. Okay? But I'd rather get to the examples for now, but feel free to ask if you have any questions. So the first example I want to look at is suppose A and B satisfy x squared minus 18x plus 18, I should have wrote is equal to 0. Determine a squared plus b squared. Okay, but the point of this is to not use, not factor this or use the quadratic formula, but use what you know from Vieta's formulas to determine this. Okay, so I'll give you a minute or two and try and work this out. So again, the point of this is to not use the quadratic formula and rather use Vieta's formulas. And here, using the quadratic formula would get really ugly because the roots are not integers, right? Because I think this doesn't factor with the regular factor techniques that we've seen, if I remember correctly. Okay. Instead, what we do is we know that the sum of the roots has to be 18, and the product of the roots is also 18 in this case. Is that clear? Right. So we have the sum of the roots is 18, and the product of the roots is 18. We know the expansion of a plus b quantity squared will be a squared plus b squared plus that 2ab middle term. I'm trying to solve for a squared plus b squared, so I rearrange and write it as a plus b quantity squared minus 2 times a times b. And I know what each of these intermediate terms are from Vieta's formula. So I have 18 squared minus 2 times 18. And that gives me 288. So that's how you find a squared plus b squared without having to expand out and find out what the roots themselves are. So this question sort of illustrates the power of using Vieta's formulas. Now you may ask, sure, it's cool for this math question, but what is the real power? It's your intellectual enjoyment. That's about it. So is everyone clear on what we did here? We used Vieta's formulas to express a plus b and a times b, and then rearrange a plus b quantity squared so that we could get something that we wanted. Any questions with this example? Cool. So the next one I want to look at is suppose this polynomial x cubed minus ax plus 15 has 3 real roots, 2 of which sum to 5. What is the absolute value of a? So again, I'll give you a couple minutes to discuss amongst yourselves and try and work this out, and then we'll take it up. And so the one thing you're supposed to notice is that the coefficient on x squared is what? 0. Okay, so think about what that means. So we know the coefficient on x squared is 0, which tells you what? That the sum of the roots has to be 0. Okay, so we know that 2 of the roots sum to 5, so let's just say r1 plus r2 is 5. That tells you right away what the third root is, right? Negative 5, because the sum of them has to be 0. We also know that the product of the roots is what? Negative 15, right? And so what we can do is we know that this negative a term will be equal to this weird combination r1, r2, r1, r3, and r2, r3, right? What we can do is factor out an r3 here. So we have r3 times the sum of r1 and r2 times the product r1 and r2. And then instead of writing the product r1 and r2, because we don't know what r1 and r2 are individually, we just know that they sum to 5. What we can do is rewrite this last term, r1, r2, as r1, r2, r3 divided by r3, right? And the reason we do this is because we know what r3 is. It's negative 5. We just don't know what r1 and r2 are individually. So what I do is I write this as r3 times quantity r1 plus r2 plus r1, r2, r3 divided by r3, and then I plug in the values I know. I know r1 plus r2 is 5. I know r3 is negative 5. I know r1, r2, r3 is negative 15, and that gives me negative 22. So it tells me the absolute value of a is 22. Is that clear? So again, what we did, we had no way of figuring out what r1 and r2 were on their own, but we didn't need to, because using Vieta's formulas, we get some relationship between the coefficients and these symmetric sums, and this one R1, R2 plus R1, R3 plus R2, R3 didn't require us to actually know the values of R1 and R2 individually. We just used the fact that we knew that their sum was 5, and we were able to compute this result for A. Okay, the last question I want to go over really quick, and then we'll call it a day. Is everyone good with this? Cool. Is suppose f of x is equal to x squared plus 6x plus 9 to the exponent 50 minus 4x plus 3. Okay, so it seems kind of random, but there's a reason it's written like this. And suppose this function has 50 roots, which makes sense because it's a polynomial of degree 100, R1 through R100. Determine the sum, R1 plus 3 to the 100, plus R2 plus 3 to the 100, plus R3 plus 3 to the 100, all the way until R100 plus 3 to the 100. Okay, so I'll go over the solution right now, but right off the bat, does anyone have any ideas how we'd approach this? Yeah.
Would you first write out x squared plus 6x plus 9 as x plus 3 squared?
Yep.
So the thing becomes x plus 3 to the 100.
Good. So yeah, we definitely do that. Okay. Okay, let's just go over it. So yeah, you're right in that we factor this as x plus 3 squared. So we're left with x plus 3 to the 100. And we know that if we're looking at roots, they must satisfy the function is equal to 0. So I can set this entire thing to 0, but then subtract it over, so I'm left with just x plus 3 to the 100 on one side, and I have 4x minus 3 on the other. Okay? And so now exactly what I want is what I get when I sum this quantity for all of the roots, R1 through R100. Okay? So when I sum this quantity for all of the roots on the left, I get what I want. And when I sum it on the right, I have 4 times the sum of all of the roots minus 300. Okay? But what we're looking at are the roots of x plus 3 to the 100. From Vietas, we know that the sum of those roots is 3 times 100 choose 1, which was 300, telling us that the sum of the roots is negative 300. So we use the binomial theorem here, because the sum of roots of x plus 3 to the 100, negative 300, because I have x plus 3 to the 100 is equal to x to the 100 plus 100 choose 1, x to the 99 times 3. So I have my 300 there, and so that tells me the sum of the roots is negative 300, which tells me that this sum right here is negative 300. So my final quantity is negative 1500.